Exponents with a scanner. Can't solve it, don't panic. And it wants the all saying. Here next to the okay.
Hello everybody, my name is Christopher Kolos and I will be going over lessons 1 through 3 of Unit 3, Linear Functions, Equations, and their Algebra. Starting off with Lesson 1, we have direct variation. To simply put it, direct variation involves variables that are directly related or are proportional to each other. For example, y equals to 6 when x equals to 12. Or y equals to 2 when x equals to 4. In an ordered pair, two variables have a direct relationship if y divided by x equals to k, or y equals to k times x. K is the constant of variation. As an example, we can go back to the example above. We could put 6 or y over 12 or x, and we get 1/2 as our constant of variation. Same thing goes for the other y and x values. This is the practice question. You can pause now, read it, and continue when you think you understand this question. So for part A, we know that Mr. Iskander on a normal day is happy, normally happy, and he gives us 10 minutes. So let's write this down. I used 100% happiness. You could use any value other than 0. Hopefully it's positive. So, part A says that when Mr. Iskander is twice as happy, how much time do we get? So let's write this down. Now, we have 100 happiness, which is him on a normal day, times 2, we get 200% happiness when he's twice as happy. Now, for anyone above the 2nd grade, they could figure out that since you multiplied this side by 2, you could most likely multiply the other side by 2. So you could get 10 times 2 equals to 20 minutes. But for everyone who likes to make life hard, you could use a method called cross multiplication, which means that when you write these as a proportion or as a fractions, you multiply the numerator of one times the denominator of another, and the denominator of the first fraction by the numerator of the other fraction. And let me write this out for you. So this way we can combine whatever we can combine. I personally dropped the units because it's less of a headache, but please use units on your exams. So solving for x, we get x equals to 20, meaning that when Mr. Iskander is twice as happy, we have 20 minutes to solve the problem. Now part B says that when Hardeep walks in late, Mr. Iskander becomes half as happy. So let's write this down. This is Hardeep, and we have everything written down now. Now I just used the first method, easily multiply 10 by 1/2, we get 5 minutes. Moving on to lesson 2, average rate of change. It is the rate that the output is changing when compared to a change in the input. So this is basically known as average slope. Now rate of change, also known as slope, can be found by using the formula y2 minus y1 divided by x2 minus x1. This is an example. You could read the question, and I'll give you a moment. Alright, so the first thing I did, look at the graph, find my coordinates. I got the 4, I got the 7, and I got the y values that they are at. I put it into the formula, simplify it, and now I know that the average rate of change over the domain interval is 1. Now, if you look on the graph, it doesn't look like it's 1, but this would be the average. This is a hypothetical line. We could put this into a real-life example. A car is at a complete stop, and when it starts, it takes the car 5 seconds to reach 50 miles per hour. So The question asks to find the average rate of change over this domain interval. So the same as the last example. Find the coordinates, put them in the formula, simplify, and find the average rate of change. Now, lesson 1 was simple, lesson 2 was simple, lesson 3 will also be simple. Lesson 3 is forms of a line. This lesson will specifically talk about two forms of linear functions, slope-intercept form and point-slope form. Now, x1 and y1 are a set of coordinates on the linear function, and you will need this for your point-slope form. Now, there will be many questions in Algebra 2 that will require you to put your answer in one of those forms. Here's an example. This was a question from Regents. Now, I want you to take a moment to read it. Now, what can we take from the info that was given? We can take that the equation we are looking for is parallel to the equation that was given in the question. We also are given that our equation goes through the points 6, -8. And if you look at all the answers, they are all in point-slope form. Now, this info is more than enough for us to solve the problem. Since the equation we are looking for is parallel to the one given, it will have a slope of 3/2, meaning that we can eliminate choices 1 and choices 4. Now, since all the answers are in point-slope form, we have to put in a set of coordinates that lie on our line, and we were given them, 6, -8. So after inserting these coordinates, we get answer choice C, which is correct. Now, this is the end of lessons 1 through 3, and we will begin with lesson 4 shortly.
I know you miss seeing me in class, so here I am, Okay, welcome guys, Unit 4, Lesson 4 and 5. And I don't know why Christopher Colas put his name there in black right here. I don't know if you guys can see it. He's crazy, but it's okay. So Lesson 4 is linear modeling. What is it? It sounds, linear modeling is the modeling of a linear function, which are functions that are a constant rate and which one variable changes with the respective other. It is the ability to create an equation or a graph of a different situation every single time. For example, snow melting. This is the example that we have today. Dia was driving her car from New York City at a constant rate of 58 miles per hour. He started 45 miles away. There's two parts to this question, part A and part B. Write a linear function that gives Dia's distance from New York as a function of distance D from New York as a function of the number of hours H he has been driving. And B is if Dia's destination is 270 miles away from New York, algebraically determine to the nearest tenth of how long it will take to reach Dia's destination. So now we're going to solve this. I know you're kind of confused, but here we go. Okay, so for part A, we first have to create the formula. By creating the formula, this is the formula that we come to. D equals to 58x plus 45. You might be asking why. Okay, since the constant speed is 58 miles per hour, that's the x value, and it's over 1 hour, this is the y value, this is the x value. So we have this now. New York is 45 minutes away, so we added 45 to the equation. So D is the distance, 58 is the rate of change, x is the variable, and 45 is the distance. So that was simple. If you have any questions, I'm sorry, but I can't help you. Okay, part B. If she was 270 miles away, that's what the question is asking. So this is pretty simple. They're asking us about distance, and we have D in our previous equation. We just plug it right back in. So it says if she was 270 miles away, we add it. Distance plug into the original problem. 270 equals to 58x plus 45. We just solve this out, and we get 3.9. So 3.9 hours. Here, I'll pause it for a sec so you guys can take a minute. Okay. So lesson 5, an inverse function. This is inverse linear functions. An inverse function is a function that performs the reverse of another function. For those of you who don't know, there are two simple steps. Step 1, switch the x and the y. 2, step solve for y. And right here is an easier way to understand it. I'll wait another second if you guys want to check it out. Okay, so this is the question that we have. On the grid, the linear function y equals to 2x minus 4 is graphed with the line y equals to x. We can go back and forth to the questions just to see what they look like. So for question A, how can we tell if y is a one-to-one function? Really easy. Since x is not to the second power, or x is actually to the first power, then it's a one-to-one function. For part B, we see it says graph the inverse. This is really easy because all we have to do really is just flip the equation around, change the x and the y's, and solve for y. And here we go, that's graphed. Give it a second. Okay, moving on to part C. It says what can we say about the graphs y equals 2x minus 4 and its inverse with respect to the line y equals to x? We can say they are reflections across the line y equals to x. When we go back here, we just see they're reflecting over this exact line right here. Y equals to x, since they are inverse, they are reflecting over it. Part D is really simple. It says, find the equation of the inverse of y equals to mx plus b form. And here it is. And for this question right here, this is really, really simple. When we go back to this step for part B, instead of simplifying it to this, we just add the step here. So it would equal to x equals to 2y minus 4 over 2. Well, I hope you enjoyed this lesson.
6 of Unit 3. Lesson 6 talks about piecewise linear functions, which are functions that have different equations for different portions of their domains. In a piecewise function, you use one formula when your domain is in the range of that piece. For example, -2 is in x is less than 0, and 4 is in x is greater than or equal to 0. This is a question that was pulled out from a region. Pause the video, read it, and try to solve it on your own. Part A asks for us to find the y-intercept of this function algebraically. The x value of the y-intercept is always 0, meaning that we use the formula y equals 5 minus x. You substitute in 0 and get a y-intercept of 5. Part A also asks why a function can only have one y-intercept. A function can only have one y-intercept because on a graph there is only one 0, which is the x value for the y-intercept. Moving on to part B, it asks us to find the x-intercepts, also known as zeros. The y value of x-intercepts is 0, so substitute that into each formula and you get x equals 5 and x equals -4. Part C asks us to create a graph, which is shown now on the screen. Part D asks why our graph contradicts our answers from Part B. Well, the graph contradicts the answers from Part B because the zeros would have been on the graph if the function was not cut off at a certain x-coordinate. This means that since the functions had a set domain, they could go on, and the zeros were not in that set. They don't show up on the graph. Part E asks, how can we resolve the fact that the algebra seems to contradict our graphical evidence of x-intercepts? One possible resolve is to temporarily remove the set domains to see if the function has the same x-intercept that we have algebraically calculated. This is the end of Lesson 6.